Time for us to do some problems involving parameterized curves. As we go through and do the applications, you're certainly going to get a sense of like, hey, this feels kind of familiar. Because applications, once you have the basic formula, the principles are still the same. So it's just a matter of applying it in this new setting. So we're going to do a lot of problems. And the more that we do, the better that we get. If you're following along and doing problems, make use of the pause button. See a problem you like? Try it out on your own first. See how far you can get. If you ever get stuck, you can unpause and up to the point where maybe you're like, I see how to go. Pause me again. And I'm like, okay, then keep working. The more that you do, the better that you get. And once you get the hang of the setup, a lot of it's just getting used to the algebra. So practice, practice, practice. Well, that reminds us, we should start practicing. Let's begin. Our first problem. Find the length of the parametric curve, t to the 4/3 cosine log of t, t to the 4/3 sine of log of t. Wow, what a curve. Okay. Well, length of parameterized curves, there's a basic formula. And it says the following. Length is adding up, start to stop, the square root of, and then you take the x prime squared plus the y prime squared, and you integrate that dt. All right, that's our formula. 90% of the work in arc length problem for parametric curves is trying to figure out a way to simplify this square root expression. So let's do that. Now that's almost all of that is algebra. And of course there's a little bit of derivatives at the start, but it's being careful. Be careful with your derivatives, be careful with your algebra, and be patient. Don't try to rush through it. So here we go. Let's just start by looking at x prime squared plus y prime squared. We want to see, does that have a nice expression? So what happens? Well, we're going to have to take the derivative here, that's the product rule. Derivative of the first term, 4/3 t to the 1/3 cosine log t. Derivative of the second term will be, well, so derivative of the first times the second, t to the 4/3, derivative of cosine minus sine of log t, times by the derivative of log t, 1 over t, because you have to use the chain rule, squared. That's x prime. Don't forget, you also have y prime squared. I'm going to write it underneath here. So similar process, 4/3 t to the 1/3 sine of log t, derivative of the first times the second, plus t to the 4/3 derivative of sine is cosine log t times derivative of 1 over t squared. All right. Good. Good. Now, does anything nice happen? Well, yeah. You'll notice here you have a t to the 4/3 and a 1 over t. So what you can do is you can take the 1 over t and put it in. This makes this to the 1/3 power. Same thing happens on the other term. See that 1 over t to the 4/3. That makes this to the 1 over 3 power. And now we say, well, great. Look, everything has a t to the 1/3, right? T to the 1/3, t to the 1/3, t to the 1/3, t to the 1/3. Everything has it. So you can imagine we just pull it out all the way out in front. Remember, it has to be squared. So when you take t to the 1/3 squared, that'll be t to the 2/3. Remember, you multiply. So we get a t to the 2/3. And now we're going to get a lot of other stuff too. So time for us to be patient. We're going to square this, so that'll be 16/9 cosine squared log t. The cross terms, well, there's a cosine and a minus sign, and don't forget the 4/3. So it'll be minus 8/3, y8. Remember, a minus b squared would be 2ab in the middle, so that's 2 times 4/3. Cosine log t sine log t. All right. Then plus sine squared log t. Okay, so that's the first term squared. The second term squared, 16/9 sine squared log t. Then the middle term will be plus 8/3 cosine log t sine log t. And then the last term will be a cosine squared log t. Okay. Whew. Now, the good news is it looks like we have some cancellation about to happen. Look at the middle terms. A minus 8/3 cosine sine, a plus 8/3 cosine sine, those cancel. But there's even more good news. Look in the end. You get sine squared plus cosine squared. Well, that equals 1. Right? Sine squared plus cosine squared equals 1. And here, what do you have? Well, similar thing, except there's a factor of 16/9. So that equals 16/9, right? Because 16/9 times cosine squared plus sine squared. Aha! Great! Well, and the good news keeps coming. Because what do you see? Well, what we have now, we have t to the 2/3, 16/9 plus 1. Well, that's 9/9. So this becomes 25/9, t to the 2/3. Now that's inside the square root. Well, you'll notice this is the same as 5/3 t to the 1/3 squared. Because we can, every piece it really has a square attached. Now, we're in great shape to finish up. Beautiful shape, really, if you think about what's left. Because what do we need to do? Well, we need to integrate, start to stop, 1 to 8, the square root of this expression. So the square root of this expression is 5/3 t to the 1/3 dt. All right, well, when we integrate, what do we get? That's 5/3, and we're going to add 1, so that'll be 4/3, multiplying the front by 3/4, the reciprocal. And evaluate 1 to 8. The 3's cancel. So we really have 5/4, and then we have 8 to the 4/3 minus 1 to the 4/3. Well, 1 to the 4/3 is easy, that's 1. How about 8 to the 4/3? Well, the best way to do that is start with the cubed root of 8. Cubed root of 8 is 2. Now take 2 to the 4th power. So you get 2, 4, 8, 16. So this part is really 16 minus 1, which makes it 15. 15 times 5/4 gives us 75/4. And we're done. It worked out very clean. And so this is a case. It often happens when you see cosine and sine that when you square, it's like, oh, look for that cosine squared and sine squared combination so that things work out beautifully. And here it did. But it was because we were very careful with our algebra. If things hadn't been canceling out nicely, so that we would have something that looked impossible, well, we would stop and say, whoa, hold on, let's take a step back and let's be careful and see if we haven't made a mistake. So, good. I think we're good on this one. Let's try another one. So, our next problem. Find the length of the parametric curve below, where time goes from 0 to pi over 2. And x is 4t cubed minus 2t plus sine 2t, and y, 8 times root 3 times t cosine t minus sine t. What an interesting expression. Well, let's dig into it and let's see what happens. Now we know our basic formula. When we're looking for length, arc length, add up, start to finish, and then for parametric curves, it's the square root of x prime squared plus y prime squared. Okay, so we're really going to spend most of our time working on what's happening underneath that square root. fingers crossed, we're going to get a square. Well, we won't know until we get into it. So let's start digging into it. Let's see what happens. So we begin. Let's first find x prime. So that would be 12t squared, and then minus 2, then plus 2 cosine of 2t. Okay, how about y prime? Well, there's a factor of 8 root 3. We can just pull that out and then take the derivative here. Derivative of the first times the second, cosine t. Then plus t times the derivative of cosine, negative sine. So, and then minus derivative of sine. Well, that's minus cosine. We say, okay, well, we have some good news. Some great news, actually. You'll see, aha, we can cancel some cosines. Great. Woohoo! Good. Good news for us. Good on us. Good on us. So this term right here is really minus 8 root 3 t sine t. Now, before we go further, we have to think about something going on here. First off, if we square that, that's going to be a mess. But, okay, look, messes sometimes happen. But there's another issue. Look a little closely here, and I think you might notice this. Here we have 2t, and there we have t. They're kind of incompatible. We'd really like, if we're going to have trig functions, we'd really like the insides to match. If the insides match, that means that we can directly compare or put things together. So we start thinking, okay, is there a way to rewrite cosine of 2t that is sort of a simpler, easier to use expression? And as a bonus, we want to get rid of the 2t, and if we can connect it to sine, then we're in great shape. Well, we don't have to look too far. Turns out that there's a set of lovely identities. They're called power reduction. So let's sort of recall them. Of course, there's only like 6 trig identities you need to know. And, sine squared plus cosine squared equals 1. Tangent squared plus 1 equals secant squared. Sine 2t is 2 sine t cosine t. Cosine of 2t is cosine squared minus sine squared. And if you use that one, you actually come up with the following. And I'll just write it. This is the way we oftentimes think of it. Power reduction. Sine squared is 1 minus cosine 2t over 2. And cosine squared is 1 plus cosine 2t over 2. Now, we look at this and say, oh, hey, hold on. We can rewrite cosine 2t in terms of sine of t, just normal t. So, this in particular says, if you clean it up, it says that cosine of 2t is what? Well, double, and then you move things around, is equal to 1 minus 2 sine squared t. This is also just the double angle formula for cosine. So, I like this because if I replace cosine 2t with this expression, everything's in terms of just sine of t. So, let's do that, and let's see if anything nice happens. So, updating x prime. What do we have? Well, this is 12t squared minus 2 plus 2 times this. So, plus 2 times 1 minus 2 sine squared t. Now, we say, aha, something beautiful happens. Notice, when you distribute it through, you're going to have a plus 2, and there's a minus 2. Cancel. Perfect. So, what else do we have? Well, we still have the 12t squared, and this other term, minus 4 sine squared. Good, good. Okay, now, let's look at x prime squared plus y prime squared. Let's see what we get. Excuse me. All right, so when we do x prime squared plus y prime squared, we're going to get the following. We'll square this term. So we'll go ahead and just square it right now. So that's 144 t to the fourth. The cross terms, so that's, this is the a squared minus 2ab. Well, be careful here. Minus 2 times 12 times 4. Okay, that's 2 times 12 times 4, 96. Okay, that's a strange number, but all right. Yep, this is t to the fourth. T squared squared. Now minus 96 t squared sine squared plus 16 sine to the fourth. Okay, that's x prime squared. How about y prime squared? Well, the minus goes away. 8 squared is 64. 64 times 3 is 192. Okay, so add 192 t squared sine squared t. And now we're like, wow, perfect, perfect. Because look, what happens? Minus 96 plus 192, you get a nice combination. So it becomes 144 t to the fourth plus 96 t squared sine squared t plus 16 sine to the fourth t. And now we say, whoa, that's amazing. It's really amazing because this expression is almost identical to that expression. The only difference is that instead of a minus, it's now a plus. Well, this was an a minus b squared, so that means this is an a plus b squared. So we get the following. This becomes 12t squared plus 4 sine squared t squared. Good. Good. Now we're ready to go. Okay. So we see, aha, lo and behold, our arc length is, when we do x prime squared plus y prime squared, it's the square root of a square. So we can say the following. Our length is equal to the integral a to b, 0 to pi over 2. Square root of the squared makes 12t squared plus 4 sine squared t dt. And now we just have to integrate that. Well, the 12t squared, easy, easy. But what about 4 sine squared t? Well, there we can use our identity. In fact, we have it available right here. You see 4 sine squared t, we can replace it. If you multiply by 4, that's equal to 2 minus 2 cosine 2t. Just multiply this, both sides, by 4. So we say, okay, great. So we now have, this is really the integral, 0 to pi over 2, the 12t squared plus 2 minus 2 cosine 2t dt. All right, integrate. Integral 12t squared, well, you'd add 1, get t cubed, divide by 3, which will give us 4t cubed. Okay, plus 2t. And then here, when you integrate, well, integral cosine, positive sign, so there's still going to be a minus. And so it'll be sine of 2t, but we need to divide by 2. Well, there's already 2 there, so that would leave us with a minus sign of 2t. Now, we're almost there. We still have to evaluate. The good news is when you plug in 0, what a great number, 0. 0, 0, 0. So we plug in pi halves. Pi halves cubed, well, times 4. If you take a half cubed, it's an eighth, times 4 leaves you with a 1/2 pi cubed. Okay, this 1/2 is really 4/8. 2 times pi halves, well, is pi. Sine of pi, 2 times pi halves, sine of pi is 0, goes away. And therefore, our final answer, 1/2 pi cubed plus pi. Wow, what a great answer. What a fun problem. What a fun problem. A lot of like, okay, learn to use your trig identities and be careful. And a lot of the, this idea of like, well, why did we change this cosine 2t to something else? Try to make the trig functions compatible so that the insides match. Now, we could do it at any point, but one of the things is, if you know you're going to do it early. The sooner you start, the more likely it is that it'll be simpler later on, because a small substitution at the beginning to simplify is a lot easier than having to substitute in many places after you do some sort of operation. So, all right. What a problem. Great stuff. Let's do another problem. Okay. Find the length of the parametric curve 7 cosine t minus cosine 7t and 7 sine t minus sine 7t, where time goes from 0 to pi. And here is this beautiful picture. And you can actually trace it out. It's not so hard to see. If you, for example, plug in time equals 0, you'll get 0 for the y. And over here, you're going to get 6. So you start here at 6. And you're going to move along here. Doesn't matter when we're talking about arc length. And you end up here, when you plug in pi, cosine of pi is -1. So you end up with -7 minus -1. And so you end up here at -6. So we're going from 6 to -6 in a very roundabout way. All right. Well, this looks a little bit simpler. And they even gave us a hint. And I suspect it's going to be useful. It says, look, if you see something like cosine alpha cosine beta sine alpha sine beta, it's cosine alpha minus beta. Well, I suspect that will be a useful hint as we move forward. Let's see what happens. Well, we do what we always do, which is we think about our basic formula. We know our length is adding up, start to stop, square root of x prime squared plus y prime squared dt. So we're going to spend a lot of time here with our x primes and our y primes. Now, they're not so bad. For example, x prime, well, derivative of cosine is negative sine, so minus 7 sine t, and here, be minus is a plus, and then a sine of 7 times t, but chain rule says put another 7. Y prime, what's that? Well, derivative of 7 sine t is 7 cosine t, and then what's next? Well, minus, and then here be 7 cosine 7 times t. Okay, good. Well, now we start digging into it. Let's see what we get. When we square x prime squared plus y prime squared, well, we're going to get, so squaring that up, well, notice everything has a factor of 7. So imagine I just pull all the 7s out. So there's 7, 7, 7, 7. It's all being squared, whoosh, all to the front. Okay, so let's just put that right there at the very beginning, 49. Now, we square. Minus sine t squared, positive sine squared. You have the cross terms, minus 2 sine t, sine 7t, and then plus a sine squared of 7t. Okay, the 7s are all out in the front. That's why we don't keep writing 49 over and over and over again. Okay, that's x prime squared. Underneath it, we'll put y prime squared. So, cosine squared. All right, that's good. The cross terms, minus 2 cosine t, cosine 7 times t, and then on the end, minus squared plus cosine squared of 7 times t. Okay, good, good. Now, what comes next? Well, we clean it up. The sine squared, cosine squared, easy. That's 1. And a similar thing happens on the other end. Sine squared of 17, cosine squared of 17 is also 1. So that's 1, and that's 1. Now here, what do we have? Well, so it's minus 2 times something. Well, it's sine t sine 7t, cosine t cosine 7t. It's exactly what you see here. Sine alpha, sine beta, cosine alpha, cosine beta. So it becomes cosine of the difference. It doesn't matter whether you take t minus 7t or 7t minus t. Cosine is an even function, so it doesn't matter if you negate the inside. So we'll write it as cosine 7t minus t. All right. Good. Good. So what do we end up with? Well, we now have 49 times, well, 1 plus 1 makes 2 minus 2 cosine of 6t. Okay, now that's not so bad. But we'd like to wonder, we'd like it to be even better. And what do we mean by better? Well, we'd like it to be a square. Or, at the very least, now I have 2 terms. And so we start thinking, well, is there any identities? And for that, we have sort of power reduction identities. Now, what are they? Well, they are the following. Sine squared t, 1 minus cosine 2t over 2, and cosine squared t is 1 plus cosine 2t over 2. Oftentimes, when we use power reduction, the name implies, the idea is we want to reduce the power. But there's nothing that says we can't go backwards. We can say power increasing identities. So what do we mean by that? Well, what it says is we can increase our degree. Look closely here. See, this 2 minus 2 cosine 6t is very close to what we have on this side. If you were to multiply both sides by 4, and by the way, I probably chose a bad notation here when I wrote down t. It doesn't matter what symbol you use here. So I'm going to change my symbol just for a second. Instead of writing t here and t here, I'll write something else. Let's do theta. So if I multiply both sides by 4, that says 4 sine squared of theta is equal to, on this side, 2 minus 2 cosine of 2 theta. Great. We say you have a 2 minus 2 cosine of something. We can call theta to be 6t. So what does that say? It says that this piece right here, we can rewrite it. So it's 49, and this becomes a 4 sine squared of, here we got to be careful. Okay, so 2 times our theta is 6t. So theta should be 3t. All right, great, good. Now we're really happy here. Okay, because our inside term, that square root x prime squared plus y prime squared, really is the square root of something which is a square. Our best possible outcome. Okay. So here we go. What happens? Well, so we have our length will be integral 0 up to pi. We take the square root here. The square root here, well, take the square root of each piece. There's a 7, a 2, and a sine of 3t, right? Okay. Well, that's not so bad. We can integrate that. What do we have? Well, 14 integral of sine is a negative cosine of 3t, and divide by 3. So you have to keep track of the inside. Well, evaluate that from 0 to pi. And if we're careful here, and we'll be careful, so that's 14 thirds, and when we plug it in, well, cosine 3 pi is negative 1, so That's minus 1. And subtract, we can plug in 0, we'll get a minus 1. So really it's 1 plus 1, which is 2, which is 28 thirds. Good. Now, let's think about this answer. This is kind of interesting here. 28 thirds. If you take 28 thirds, that's equal to 9.333. And you're like, okay, all right, cool, whatever. Hold on. Let's look at our curve. We started here at 6, and we went over there to negative 6, and we moved around here. How far apart is it between negative 6 and positive 6? It's 12 apart. So how is it possible that when we moved along this curve, that we started at some location, ended up at some other location, that it took us less length to get there than if we had gone in a straight line? That doesn't seem right, because it's not right. It's not possible. It's not possible to take a shorter trip than going in a straight line. Somewhere a mistake has been made, or we've broken laws of math. Now, I'm one who is convinced that we won't break laws of math. Actually, there was a mistake made. I deliberately made this mistake. See, normally when I make mistakes, they are not deliberate. But there was a very deliberate mistake made here. So, can you see where it was? I'll tell you where it wasn't. It was not in the formula. That's the correct formula to use. It was not in our simplification. So, this side, everything's correct. But then you're like, well, yeah, but the integration is fine. There's no place left for a mistake. There is one place. We took the square root. Square root of 49 is 7. Square root of 4 is 2. Square root of sine squared is not sine. Now you're probably thinking, I'm pretty sure it is sine. It's actually the absolute value of sine. So that was the mistake. Now, sometimes it doesn't make a difference and sometimes it does. What's happening here is if you graph this function, the absolute value of, well, the sine 3t does this between 0 and pi. So normally a pi, it would just only have one up and down. But because of that factor of 3, it increases how many times you go up and down. So what really happens is when you have absolute value of sine 3t, is it should be doing this. Because we're only doing sine, we forgot to do the absolute value. We had a negative part, and thus we got some cancellation. So this is not the right answer. But the good news is it's easy to correct. Once we understand why we made our mistake, we say, okay, what happened was we should have had an absolute value. And now we say, well, we understand the sine function. And therefore, what we'll do is, instead of doing this, we're just going to 3 times, and we're just going to do one piece from 0 to pi over 3. And everything else works out perfectly fine. Because if I only do that part, then I can truly drop the absolute value. And so we do. When we integrate this, well, we'll end up with a 14. There's a negative because the integral of sine is negative cosine. And lo and behold, we see that the 3 here would cancel with the 1/3. Evaluate from 0 to pi over 3. And we get negative 14 times minus 1, subtract minus 1, which leaves us with a grand total of, subtract just positive 1, because of that minus 14, which leaves us with a grand total of 28. We probably could have seen it earlier if we just multiplied the previous answer by 3, because we had cancellation. So that instead of doing all 3, we really had the equivalent of just 1. All right, well, what's the moral? Be careful. When you take a square root of a square, you should say, hold on, do I need to worry about some signs here? If you go back and look at the problems, every time when we had square roots, everything was positive, so we were okay. but it may not always be the case. So, a word of warning, a cautionary tale. What an interesting thing to happen. All right, well, good. Well, let's do a problem now with a different application. We'll do area. Find the area bounded by the x-axis and the cycloid curve, which is given parametrically by t minus sine t and 1 minus cosine t. And that's the picture of the curve. Now you might wonder, well, where does this curve come from? Well, where it comes from is the following. You can imagine that you start here and that there's a wheel centered along here, and you have a point right there. And now what we're going to do is we're going to take that wheel and we're just going to push it along. So it's along the ground level, so we push the wheel along, and what happens is that the wheel continues to turn. And as the wheel turns, the point that we've marked is going to rotate around. So it initially is going to go up, and it's going to eventually come along, peak up, start moving down, and eventually, after a full revolution, it would get back to the ground level. So if you were to then sort of say, okay, trace out where that point went in space, well, it would do that shape. So that's where that curve is coming from. It's following a point on a spinning wheel. Now, we say, okay, well, that's the curve. Well, what's the area? Well, how does the curve move? Well, what happens, you can actually figure it out. Think about what happens at time 0. You're at the x-coordinate 0, time 2 pi, where you're at x-coordinate 2 pi. So we move in this direction. So we say, all right, what's the area? Well, our area is going to be adding up, start to stop, our height and our width. Now, what's our height? Well, we're really thinking of these as little tiny rectangles here. So our height would be the y value, so that's the y of t. What's our width? Well, that's how much we have our x value change. So that's this part. So it's not the dt, it's the x prime of t dt. Because t is not a length measurement, think of it as a time measurement. We have to convert that somehow into a length measurement. And we do it by saying, oh, well, since dt is a time, if we times it by a rate, then, distance over time, we get a length. So that's what the x prime t dt does. So for us, we have, this is integral 0 to pi. Well, what's y of t? 1 minus cosine t. What's x prime of t? Well, take the derivative. That'd be 1 minus cosine t dt. Okay, so there we go. That's what we need to integrate. Well, that doesn't seem so bad. Not yet. Let's get a little bit into it and see if anything nice happens. Well, we square it, and it's 1 minus cosine times 1 minus cosine, it's a square. 0 to 2 pi, that'll be 1 minus 2 cosine t plus cosine squared t dt. Now the first part, 1, beautiful. We can integrate that. The second part, great. The cosine squared, well, but that's okay. You see, we don't integrate cosine squared. We say, let's look for a way to rewrite it. So for us, we can say, look, cosine squared, that's not so bad. There's something called power reduction. So cosine squared is really 1 plus cosine of 2t all over 2. So we can replace this cosine squared by this expression. Now, if we do that, what do we have? Well, if we carry this out, there's a 1 and a half. So that makes 3 halves. Then we have the middle term, minus 2 cosine t, and then plus a 1/2 cosine 2t. Okay, well, we're most of the way there, actually. We now integrate. So integral of 3 halves, that's so straightforward, that's 3 halves t. Integral of cosine is sine, so we get minus 2 sine t. Integral of cosine 2t, well, it's a sine of 2t, but you need to divide by 2. There's already a divide by 2 there, which makes this a 1/4. And all of that needs to be evaluated from 0 to 2 pi. Okay, well, what happens? Plug in 2 pi. 2 pi times 3 halves. Well, that would be 3 pi. Sine of 2 pi, 0. Sine of 4 pi, 0. Plug in 0. 0. 0. Yeah, okay. Sine of 0, 0. Sine of 0 again, still 0. So everything drops out except that one term telling us that that shape has a beautiful area, 3 pi. And we're done. Wow, that's a great shape. Beautiful. 3 pi. Well, interesting. I wonder if there's anything else we can do with our curve. Well, let's do this. Here we go. It's the same curve. It's the cycloid, right? So it's t minus sine t, 1 minus cosine t, and we're going to find the surface area, which results when we spin it here around the x-axis. So now we're after the surface area. Well, can we do it? I think so. What do we do? Well, let's think about our generic surface area setup. Our surface area is what? Surface area is adding up, start to stop, 2 pi, radius, and length. Okay. Well, our radius, the idea is we're going to chop into little pieces. We go down here to the x-axis. So our radius would be our y of t, which is 1 minus cosine t. All right, well, that's great. What about the length? Okay, so that is probably where we're going to spend most of our time on this problem. So let's think about what happens here. What is the length? Well, we're going to take x prime squared plus y prime squared. Because remember, the length is the square root x prime squared plus y prime squared dt. So we need to figure out what's happening with x prime squared and y prime squared. Well, the derivative of x is what? Well, it's 1 minus cosine t squared. Derivative of y is sine of t and squared. All right, well, what does that become? It becomes 1 minus 2 cosine t plus cosine squared t plus sine squared t. Now, cosine squared plus sine squared. Beautiful. So that becomes a 1 on the end. There's another 1 there. That gives us 2. So 2 minus 2 cosine t. Now, what would we like? We'd like for this to be a perfect square. And we say, okay, is there any way to make things into a perfect square? Well, there is this nice identity called power reduction. So remember, how does it go? Sine squared is 1 minus, let's call it sine squared theta. 1 minus cosine 2 theta over 2. And cosine squared is 1 plus cosine of 2 theta over 2. That is a really poorly written cosine 2 theta, but you know what I mean. So we look at this and say, hey, it's not so far off from that sine squared. Notice, if you multiply by 4 sine squared theta is 2 minus 2 cosine of 2 theta. Well, that's something like what we have here, 2 minus 2 cosine of t. So if t is 2 theta, theta is half t. So this is equal to 4 sine squared of 1/2 t. Great. Good. Okay. That means that we can simplify, and so we say, aha, our formula for surface area is what? Well, adding up, start to stop, 0 to 2 pi. Our radius, 1 minus cosine t, and then take the square root. Well, square root of 4 is 2. Square root of sine squared is sine. Now, if you've been watching all the way through, you might say, whoa, I remember an example not so long ago when we took the square root of sine squared and we're like, don't forget the absolute value. So, okay, let's check. When do we need absolute value? Well, we need absolute value if what we're dealing with could be negative. So let's think about sine of 1/2 t. Now, sine is positive if we think of it in terms of the unit circle. So you have your unit circle. So here's our unit circle. Sine is positive from 0 to pi, okay, the top half. We're going time from 0 to 2 pi. 1/2 t goes from 0 to pi, which tells us that this piece right here, the sine of 1/2 t, is always positive for the place where we're interested in. In other words, between 0 and 2 pi. So we don't need to worry about the absolute value. It was good that we checked. But now we're fine. Okay. So don't forget there's a dt. There should always be, a d something on the end. If you forgot that, you might be missing an important part of the integral, or maybe you just forgot to write down the d something. Of course, you might have an instructor who likes taking off points if you forget that. So let's not let them get any of our points. There are points, darn it. We're going to keep them. Excuse my language. I get a little bit salty when I talk about math sometimes. All right. Well, here we go. What do we have? Well, if we distribute through, we have the following. This is equal to integral 0 to 2 pi of 2 sine of 1/2 t, right? Then minus 2 of cosine t, sine of 1/2 t, and dt. Well, the first term, we can handle that. That's not going to be a problem. The second term is a problem. If only we had some way that we could rewrite a sine of 1/2 t times a cosine t in a simpler way, especially if it had a 2 in front of it. If maybe there was a nice identity. There was a hint. Oh, right. We should use our hint. Okay, good. What does our hint say? It says, hey, look at it. If I have double sine of an angle, cosine of an angle, you take sine of the sum and add sine of the difference. Now you have to keep track what is alpha and what is beta. So in our case, this is alpha, this is beta. So what do we get? We're going to work through it carefully here. So we have, this is equal to integral 0 to 2 pi. We have our 2 sine of 1/2 t. That's our first term. Minus, okay, so we're going to have sine of alpha plus beta. Alpha plus beta is sine 3/2 t. And then sine of alpha minus beta. A half t minus t is minus a half t. Okay. Now, okay, all right. We're going to be really extra careful here. So sine of minus a half t dt. But sine is an odd function. Not to say it's an unusual function, but it has symmetry. So when I see a minus there, I can actually pull this minus out. So it goes into there. So what we can do is we can combine that sine of a half t now and this sine of a half t out in front. So what do we have? Well, integral 0 to 2 pi. There's 2 sine of a half t minus minus makes a plus sine of a half t. So 3 sine 1/2 t, and then minus sine of 3/2 t dt. And we're ready to go. The integral of the first term, well, the integral of sine is minus cosine. So it'll be a minus, cosine of 1/2 t. Now, because of the half, I need to divide by a half, which is the same as multiplying by 2. So that becomes 6. Here, integral of sine is again minus cosine, so minus makes a plus. There's a cosine, 3/2 t. But again, I have to divide by 3/2. Well, that's the same as multiplying by the reciprocal, 2/3. And evaluate 0 up to 2 pi. Well, almost there. This becomes, all right, plug in 2 pi. A half times 2 pi is pi. So multiply, cosine of pi is -1 times -6 gives us 6. 3/2 times 2 pi is going to be 3 pi. Cosine of 3 pi is -1. So this is going to be a minus 2/3. Then we're going to subtract, plug in 0. Cosine of 0 is 1, so it's a -6. And here, cosine of 0 is also 1 and a 2/3. So what are we left with? Well, we have 6 minus 2/3, and here it's, again, if you distribute the minus through, plus, and this will become minus. So it's really 12 minus 4/3 when you work it out. But if you put everything in terms of thirds, so 18/3, and then minus 2/3, plus 18/3, minus 2/3. So that's 36/3 minus 4/3 leaves us with 32/3. Now, you're probably thinking, wow, wait, where's the pi? Well, funny story, we forgot it. But we'll put it back in. See, that's our chance to say, wait, shouldn't there be something? There should. So there should have been a 2 pi. So we'll put a 2 pi here, a 2 pi there, and we just keep working our way through. 2 pi, and there's a 2 pi, and here we have a 2 pi. So there's a times 2 pi here, and so 64 pi thirds. And there we go. That's our answer. 64 pi thirds. Amazing. Amazing. Well, good. Of course, be careful. You know, you don't want to, if you're not careful, you may have forgotten to say, hey, wait, shouldn't there be a pi? Ah, yes, there should have been. Well, go back, make sure you have everything so that you get the right answer. What a fun problem. What a fun and interesting problem. All right, well, of course, more fun and interesting problems yet to come. So let's do another problem. So, find the surface area of a torus formed by spinning the circle radius 1, centered at 0, 2, around the x-axis. A torus, by the way, is just another name for a donut. So what we're going to do, what's our basic picture? Well, we have a circle here, radius 1, centered at 0, 2. So here's 2. And we're going to spin this around. So the net result is what? Well, we'll form a shape that looks very similar to a sort of a donut hole, if you will. All right, so that's our shape. Donut hole, life preserver, whatever you like to call it. But it's this sort of tube wrapped around. All right, so how do we do it? Well, we're going to just think about our formula for surface area. We have a nice formula. It should work. So we have that our surface area is adding up, start to stop, our 2 pi, our radius, and our length. Now, the only thing that we don't have is we don't have our parameterization. So we think about, let's think about this circle. It's a circle of radius 1 that's been shifted up. Now, if we just had circle of radius 1 at the origin, there's an easy parameterization. So at the origin, what do we have? It would be cosine and sine. And that's the standard parameterization for the circle of radius 1. But we've now been moved. We've shifted up our center in the y direction by 2 units. So what does that do? Well, so if our center is at 0, 2, then we have cosine t, comma, sine t plus 2. In other words, we just move all the y values up by 2. So that's our formula. Now, we say, great, what happens? Well, let's go through our length. That's usually the hard part, right? So the length, we're thinking this is our x. Here's our y. The length part is the square root of x prime squared plus y prime squared, and there's a dt. So this is the length of a little piece. Not the total length, the length of a part. Well, that's going to be the square root of, take the derivative here, minus sine t squared plus derivative here, cosine t squared. Okay, sine squared plus cosine squared. Sine squared plus cosine squared is 1. Perfect. Perfect. So this is really very clean. It's 2 pi. All right, good. Well, what else do we need to know? We did forget something about our parameterization, by the way. Let me step back before we get too far. When we have a parameterization, we need to know where are we at any given time, but also what times are we considering? So we forgot to mention our time span. So here, 0 to 2 pi, and 0 up to 2 pi. So the last thing, we know our length. What's the radius? Well, our radius is down to the axis because we're spinning around the x-axis. So our radius here is y. So this is our y of t. So we put it all together. We get that our surface area is integral 0 to 2 pi, start to stop. Our factor of 2 pi coming from there. Our radius, which is y of t, which is sine of t plus 2. And our length, which simplifies to dt. And now we're like, beautiful, we can do this, and we can, right? Well, that's going to be 2 pi, and the integral of sine, negative cosine, integral of 2 is 2t. And evaluate from 0 up to 2 pi. So we're going to get 2 pi, cosine 2 pi minus 1. 2 times 2 pi is 4 pi. Subtract, plug in 0. Cosine of 0, still 1. So there's a minus 1 plus 0. You'll notice the minus 1s cancel because it's a minus 1, subtract a minus 1, they're gone. So what are we left with? Well, we're left with 8 pi. And so there we go, 8 pi. And that's the answer. Beautiful, beautiful. All right. Well, good, good. Now, let's, whoops, not 8 pi. 2 pi times 4 pi, 8 pi squared. Forgot to see that there's a second pi. Whoops. Still, beautiful, beautiful. Nice, clean answer. Nice, clean answer. All right, well, let's do another problem. Okay. Find the surface area which results from rotating the parametric curve 1/3 t cubed minus t, comma, t squared, for minus root 3, less than equal to t, less than equal to root 3, when it's rotated around the x-axis. And so what's the curve? Well, it's this curve right here. This is our curve. Now, it's not quite so clear, what happens. In other words, which way does it go? Well, we don't really care. We don't need to pay attention. But what we see is this sort of nice teardrop shape here. So that's our curve. And we want to say, when we spin this, what's our surface area? Well, a little different. A little different. So let's see what happens. So we get the following. Our surface area is adding up, start to finish, 2 pi, our radius, and length. Okay. So we have a couple pieces here. The radius, well, that's going to be, we think of taking a piece, and how far is it down to where we're spinning? So in our case, our radius here is going to be our y of t. All right, well, that's good. What about our length? Well, that one's a little bit more time intensive. That's going to be our x prime squared plus y prime squared and dt. So, well, let's dig into it. Let's see what we have. So we get the following. Our surface area is going to be our integral minus root 3 to plus root 3. Now, we probably could go from 0 to root 3 and double by symmetry, but for now, we'll just leave it as is. And if an opportunity arises, we might rewrite it. T squared goes in for y, so 2 pi t squared square root of x prime squared. So that would be t squared minus 1 squared plus y prime is 2t squared dt. So minus root 3 to plus root 3, 2 pi, and then we have t squared, and then we have the square root of, well, t to the 4th, and then we have the cross terms, minus 2t squared, and then plus 1, and then plus 4t squared. And now I say, hey, we've seen this game before. We know what's going to happen. This part will combine with that part. And it will. And it'll combine. It'll be t to the 4th plus 2t squared plus 1. And they say, well, wait, it's basically the same thing. We just changed the sign in the middle. If it was a square before, it's still going to be a square. It's really t squared plus 1 squared. And now it's easy to do the square root. So we get minus root 3 to plus root 3, 2 pi, t squared times t squared plus 1 dt. Well, okay. Clearly, we can see all the powers are even. We have symmetry, no doubt. Not just, even if we didn't have the picture at this point, we'd say, look, we can see all our powers are even. So I'm going to double which will bring us up to 4 pi if I double 2. So 4 pi, go from 0 to root 3, and then multiply in t to the 4th plus t squared. All right, so that's 4 pi. If you integrate that, 1/5 t to the 5th plus 1/3 t to the 3rd. And evaluate from 0 to root 3. The nice thing is if we plug in 0, we get 0. So we plug in 3. Sorry, plug in root 3. Well, that might not be quite so nice. Well, let's see what we can say. 4 pi, we have 1/5. Now, root 3 to the 5th power. What we can do is, we have 5 root 3's. We can put 2 of them together. That gives us a single 3. We put another 2 together, giving us another 3. And then we have 1 root 3 left over. So root 3 to the 5th is the same as 3 times 3 times root 3. The same thing happens when you have root 3 cubed, right? So we have 3 of them. 2 of them become a 3, and then there's 1 left over. So plus 1/3 3 root 3. Well, at least here, it cancels nicely. You have a root 3. And what can you do? Well, you can pull the root 3 out. So that's 4 pi times root 3. And then, what do you have? Well, 9/5. 3 times 3 over 5. And here, plus 1. Well, that's also 5/5. All right. Well, 9 plus 5 makes 14. 14 times 4, 56. So we're going to get 56 pi root 3 all over 5. And there we go. That's it. That's our answer. It's not so bad. It's not so bad at all. Okay, so it works out kind of nicely. In this case, it was the case that our arc length compressed in a very clean way, and one of our pieces was easy to work with, so we were all able to put it together and get something nice for surface area. All right, well, let's try one more. One more problem to finish up. Find the surface area when the parametric curve t minus 2 e to the 2t and 4 e to the t, where t goes from 0 to log 2, is spun around the x-axis. All right, well, we have our formula, so here we go. Our basic picture, we have something, and so there's our curve. Just keep in mind when we're doing surface area, we say here's a little piece, and we'll go down here to the x-axis. All right, well, what do we have? Surface area, adding up, start to finish, 2 pi, radius, and length. Our radius is our y of t, which in our case is 4e to the t. So most of our work here will be length. For that, we need to look at x prime squared plus y prime squared. So that would be 1 minus 4e to the 2t squared plus 4e to the t squared. Take the derivative of x squared, take the derivative of y squared. Okay, well, what does that become? Well, it becomes 1 and then minus 8e to the 2t plus e to the 4t, 16, sorry. Don't forget there's a factor of 16. And then here, plus 16 e to the 2t. And now we're like, we've really played this game before. Look, this last term combines with that term. And we get something very clean. Very clean. So this is 1 plus 8 e to the 2t plus 16 e to the 4t, which means we get 1 plus 4 e to the 2t squared. Perfect. So what do we end up with? Well, remember the length has what? It's a square root of that expression. So this here is going to become the square root of x prime squared plus y prime squared, which for us becomes 1 plus 4e to the 2t. Now we put it all together, and we say, well, what does that say for our surface area? Well, it says the following. Our surface area is going to become integral 0 to log 2, start to stop. There's a 2 pi, and we multiply the 4e to the t times this 1 plus 4e to the 2t, which gives us 4e to the t plus 16e to the 3t dt. And we can integrate. Perfect. So we'll have, this is 2 pi, and the integral of e to the t, well, that's just e to the t. And then the integral of e to the 3t, well, that'll be e to the 3t. Then you got to divide by 3, so 16 thirds. And evaluate from 0 to log 2. So let's be careful here. This is a case where when you plug in 0, you're not going to get 0. So be careful. Be the right amount of careful. Plug in log 2. E to the log of 2 will be 2, because e and log are inverses of each other. So we'll have here 8 plus 16 thirds e to the 3 log 2. Now that one might not be quite so quick there, but if you think about e to the 3 log 2, one of the properties of log says what? Well, you can take the 3 and move it up into the exponent on the inside. So it's the same as e to the log of 2 cubed, which is 8. So this will be 16 thirds times 8. Then we're going to subtract. What happens when you plug in 0? Well, e to the 0 is 1, and still it's 1 when we plug it into the other term. So there we go. Now let's try to clean it up a little bit. Well, we can clean it up. Not so bad. Let's put everything over thirds. So that would be 64, whoops, not 64, multiplied by 3, 24 thirds. Here, 16 times 8 is, well, what can we say? 16 times 8 is 128, right? It's powers of 2. 128 over 3. And then subtract 12 over 3. Subtract 16 over 3. And all that, of course, there's a 2 pi out in front. Well, minus 12 and minus 16 is minus 28 plus 24 would get us to minus 4, which would get us, if we add 128, to 2 pi times 124 thirds. Well, 3 doesn't divide into 124, so that's as simple as we can get, other than the 2 times 124, which would give us to 248 thirds pi. And that's the surface area. And it works out. And it turned out to be a nice number in some sense. You know, we saw log 2 and like, log 2, we're going to have logs in our answer. Well, not this time. It worked out. But of course, we were always careful with our algebra. So that's the important thing. Be careful with your algebra. Make sure you keep track of terms. There was a couple times along here we forgot terms, but we said, wait, hold on. Don't forget to bring it through. And in the end, we made it. We succeeded. All right, well, keep going. Keep going. You're doing it. And I'll see you in another session.